Hello, friends. Good evening, and welcome to my YouTube channel. Uh, that is the Researcher Yugal. This is my YouTube channel, and as you all know, that I am doing PhD from IIT Mandi. At present, I am working as a senior research fellow in IIT Mandi in the School of Computing and Electrical Engineering. And at present, my research is going well. And this is my like kind of a part-time work that I do post videos on my YouTube channel. And at present, we are continuing the series of the lectures from the Boyle State. L- Let me share my screen with you all so that you can see where I am generating this content. Because in research, it is quite important to know the source code, and source should be authentic. So I'm preparing or producing or generating these lectures from electronic devices and circuit theory, which is written by Robert L. Boylsted and Louis Naschelskay. So this is my reference book, and at present we have done almost 9 lectures on this particular from this particular book, and now I have to do the uh, probably this is ninth or 10th lecture. So we have done the semiconductor diodes, we have done the diode application, we have done BJT. Now we are moving on to the chapter number 4, that is a DC biasing, BJT DC biasing. So let me move to this chapter, uh, DC biasing. So let's move on to the chapter. I'm just scrolling it down. We have to do the fourth chapter. So let me find it out. This is done. This is done. This is also done. So this is BJT. This is third chapter. Let's move to the fourth. Yeah, this is chapter number 4. Let me make it zoom so that you can see it properly. Now everything is perfect. So let's start our discussion on the biasing of the BJT. Now, first of all, you try to understand what is BJT. BJT, in the previous videos from the previous video, you can try to understand what is BJT. BJT is basically bipolar junction transistor, which has three um, terminals, emitter, base, collector, and it works in four mode of configuration. Sorry, three mode of configuration: common emitter, common base, common collector, and it works in the uh, four different types of connection can be made. That is active, inverse active, cutoff, and saturation. These are the kind of biasing for the BJT. Now let's study what is BJT biasing in detail. So let me read out the statement for you. Any increase in the AC voltage, current, or power is a result of the transfer of energy from the applied DC supply. Suppose a transistor is an active device. It has its own kind of energy. But whenever there is an increase in AC voltage, current, or the power, it means whenever the current, voltage, or the power is increased, that is, it means you're transferring the energy from one source to another. BJT have its own power, but if you're trying to change its power or increase its power, then you are trying to get the power from the supply. And here the supply is DC. That's why we are studying it as a DC biasings of the BJT. So operating point, in the previous videos, I've already told you what is operating point. Operating point is a combination of a graph between VCE, the output voltage, and the output current. So the output voltage is VCE and the output current is ICE. And the point where these 2 points meets, it is called the operating point. For example, if I draw a line like this is VCE, this is ICE. If I draw a straight line like this, and so the point here, where both the points like this, like suppose I draw one here and draw here. So this point will be the operating point. However, in this, like this way, like this way, this way. So you can see this is the operating point, 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 this is the operating. So the point at which the curve of the VCE and the ICE is meeting is known as the operating point. So you can got the idea about the operating point. Now, uh, let me move further. Fixed bias configuration. See, you can see this configuration. This is the transistor. It is called fixed bias because there is no resistance in the emitter, and this circuit is fixed. The RC and RB are fixed, and there is no there is a supply VBE. VBE is equals to zero point 0.7, and there is a supply called VCE. So if you this sort of arrangement of the circuit is known as the fixed bias circuit. If you arrange a circuit like this, in which you have RB, the base resistance, you have the RC, the collector resistance, but there is no emitter resistance, then this sort of circuit is known as a fixed bias circuit. It is one of the simplest bias circuit that we know, and it is not commonly used because the parameters of this circuit is are not very stable. They are not very thermal stable, and they does not have the high gain. So if you take out the equation from this side, VCC is equals to ICRC plus VCE, and from this side, VCC is equals to IBRB plus VBE, and you do the analysis and you find out the like VCC minus RB minus VB is equals to 0. With this, you can find out the IB, the base current, VCC minus VB over RB. And from the other equation is VCE plus ICRC minus VCE is equals to 0. Like this equation, VCC is equals to ICRC plus VCE. So it can be written as VCC is equals to VCE plus ICRC. So ICRC shifted to this side. Then you got VCE is equals to VC minus V. So you can neglect the term VE since there is no emitter resistance. So VCE is equals to VC. And VB is generally zero point 0.7, where you can find out between the drop between the VB and the VB with the multimeter. You can find out any current across the current or across the resistance with the help of the multimeter. So these are the this is known as a fixed bias circuit. Uh, and all those who are student of electronics can try to understand, and they might be trying to understand how the current through the resistance is found out, and how the voltage across the resistance is find out. Even like I'm a researcher of electronics, and I have some teaching experience as well in private engineering college, so I can easily relate to what is being represented in this diagram. And those who are student of electronics or who are the practitioner or the professor of electronics can understand what this diagram is trying to say. So that's it. This is all about the fixed bias resistance, fixed biasing. So there is a term known as transistor saturation. The term saturation is applied to any system where labels have reached their maximum value. So if the current through the transistor has reached its maximum value, it is it is said to be in saturation region. This is the basic understanding. Now, and friends and my dear students, I would like to say one thing over here, that I do post videos from on YouTube through different sources from electronics or sometimes non-technical. I have two channels. This is purely my technical channel. On this, I do post only the technical content. I have some another channel, first channel, which is a very old channel that is from 2009. This channel I made in 2026. So, considering because I have some non-technical content also, sometimes I do blogging, so sometimes I do some non-technical content also. For that, I have another channel with my name Yugal Pachori, but this channel is with the name Researcher Yugal. So this is totally technical channel because I got advice from one of the person who is an expert of YouTube. So he advised me that your previous channel is having mixed content, and it is very old channel also, that is from 2009. So you try to separate the content. So after the separation, I'm getting some advantages. So that's why I'm preparing this content from for you, and this content helps me also while preparing for the subject. So it is a two-way relation that I'm generating content for you, but it is helping me also because I'm generating the content and try to reading as well. And reading improves my knowledge, and generation is a practice for me, which another times increase my knowledges. So it's a two-way that I do get advantage from the YouTube. The students watches my channels or those who are interested in watching my channel, they do watch. And uh, and as a part of practice, it enhances my knowledge as well. So this is the fixed resistance bias. So and you can do this example 4.2 to understand the better understanding of the fixed bias circuit. Now look into the another circuit. This is again fixed bias, analysis of the fixed bias. Now the emitter bias configuration. Now friends and dear students, you can easily understood that this is RC and this is RB and this is RE. In the previous bias circuit, the fixed bias circuit, there is no RE. However, in this circuit, there is a presence of RE. That's why this is called emitter bias configuration. And by this equation, you can have VCC is equals to ICRC plus VCE plus IERE. So there is an extra term that is known as IERE. And from this side, VCC is equals to IBRB plus VBE plus IERE. So the equation is VCC is equals to IBRB plus VBE plus IERE. Okay. And other equation will be VCC. This is 4.15. And you know what is the relation between IE and IB? IE is equals to beta 1 plus IB. So you can replace IB by beta 1 plus IB, or you can replace IB, or you can replace IE. So the another equation will give you uh, IB, and the first equation will give you IB, and you can have relation between, and another this is collector emitter, this side loop, IERE plus VCE plus ICRC minus VC is equals to 0. So one equation will give you the value of the IB from like in this from this side will give you the equation of the IB, and this side equation will give you the value of VCE. So you got the IB and you got the VCE, and these are the two parameters. VC is the output voltage, and you got the IB. With the IB, you can calculate the IC. IC is equals to beta times of IB. So now you have VCE and the IC. And with these VCE and IC, you can plot the graph between VCE and IC, and hence you can get the operating point. So every biasing circuit is about to getting the operating point to do the analysis or the connection or the configuration of the transistor. So you can have VE, VC, VC, VB, and VB like this. And for example, let's take this example. For the emitter bias network, determine IB, IC, VC, E, VC, VE, VB, and VCB. So you can do one equation like this and one equation like this and do the analysis. Beta is given, all the other values are given. Just put all the values in the equation and get the results. So you can do this analysis and get the result. It is not very tough. You just have to apply the basic of the KCL and the KVL, and you can do this numerical to enhance your understanding about the emitter bias configuration. So now we have studied two types of configuration. One is the emitter bias configuration, and the first one is the fixed bias configuration. In terms of stability, the emitter bias configuration is more stable, and it has a comment also. And the comment is the addition of the emitter resistor to the DC bias of the BG provides improved stability. That is, the DC bias current and the voltage remain closer to where they were set by the circuit when outside condition. So, and they are not affected by the transistor and the temperature and the transistor beta. Although a mathematical analysis provided in section 4.12 some comparison. So you can do the analysis why this emitter bias configuration is more stable than the fixed bias configuration in the section 4.12. This you can do. And by the results, by the comparing the result of the fixed bias and the emitter bias, you can have your judgment that emitter bias configuration is more stable than the fixed bias configuration. So this is analysis. You can do the beta variation. This is the saturation level. Load line analysis, I already told you like this. I was talking about the in the starting in this video. There is a graph between VCE and IC, and there is a load line, and the point touching is known as a Q point. This is the operating point. If the operating point is at this side, the transistor operation will be different. If the operating point is on the midway, the transistor operation will be different. If it is at the lowest side, the transistor operation will be different. And on my experience basis, and due to the analysis of the transistor, the if the operating point is in the middle, the transistor is working better as a amplifier. So these are the understanding. Now let's move on to the next topic, voltage divider configuration. This is one of the important configuration in the BJT. Uh, it has arrangement like this. This is R1 and R2. So the base current is divided between the two resistors, the R1 and R2. That's why it is called voltage divider configuration. So this voltage is divided across RC and RE by the resistance R1 and R2. So you have to find out the open end resistance. Then you have to do the analysis. So the exact analysis, you have to find out the Thevenin resistance, which is given by R Thevenin is equals to R1 and R2. And if you are a student of electrical or electronics, you can easily understood there is a open circuit. And if there is open circuit, this is block, this is block, this is moving, and this is divided into this side and divided into this side. It means these two resistance R1 and R2 is working in parallel. That's why the total resistance or the Thevenin resistance is equals to R1 parallel R2, which is equals to R1 into R2 upon R1 plus R2. You can now do the analysis, move from this side to this side, and second, move from this side to this side. So in the first side, you will have VCC, VCC, this is the first location. VCC is equals to VCE plus ICRC plus ICRE. So here the current will be VCC is equals to ICRC plus VCE plus IERE, and I is equals to beta. I is equals to IC is equals to beta times of IB, and I is equals to beta 1 plus IB. So by this, you can find out the equation of the base current and the collector to emitter voltage. Again, it is analysis is quite same to the emitter bias configuration, but only there is a configuration of the voltage divider. That's why you have to do the Thevenin voltage and the Thevenin resistance. Then you have to apply again the Thevenin voltage, which is given by E Thevenin is equals to VR2, and VR2 is equals to R2 into VCC upon R1 plus R2. So IB is equals to E Thevenin minus VBE, R Thevenin plus beta 1 plus. This is very simple equation. You just need to understand the basics of this circuit, and you have to solve this configuration of the voltage divider bias configuration of the transistor that is known as a BJT. At present, this is NPN. Sorry, positive to negative, yeah. NPN. You can do the analysis for the PNP transistor also. But generally, NPN is used. Why? I told you in the previous section of the videos that NPN transistor is better than PNP because the mobility of the charge carriers of the electron is higher than the mobility of the holes. That's why NPN is better. And in NPN, the majority charge carriers are the electron, and hence their mobility is higher. That's why we prefer the NPN transistor. So I think this was the DC analysis. I told you about the three configuration: fixed bias, emitter bias, and the voltage divider biasing. So these are the important configuration. Transistor saturation, I already told you. So, and there is one more configuration, collector feedback configuration. So it means there is a feedback to the collector. So you can see there is a feedback to the collector. And this is the collector, and the base current is feedback to the collector. So this is another example. And same way you can do the analysis for the collector feedback configuration as well. So and there is a collector emitter loop configuration is also there. So that is the second part of the third configuration only. Sorry, the fourth configuration only. And emitter follower. This is the emitter follower configuration, and you can understood it and do the. This is the emitter configuration, follower configuration, common base, miscellaneous bias configuration. So this is the same analysis. Now this is the summary: fixed bias, emitter bias, voltage divider bias, volt one voltage divider bias, emitter follower, common base, and these are the design operations. So I think that's it for this part of the video. Now, with this, you might have understood what the DC biasing of the BJT and multiple BJT, because I'm scrolling because these are just the examples. You can do it by your own by understanding the basics only. And there is a current mirror circuit. So the current mirror circuit we will do in the next video. The current, I give you just some introduction to the current mirror. Current mirror follows the concept. Let me go to that point first. Multi-sim, this computer analysis. This is a summary, logic gate, alarm, practical application. So I think that's it for this part of the video. The current mirror we will do in the next part of the video. And let me summarize the video. We have done the four types of biasing: the fixed bias, the emitter bias, the collector bias, and the voltage divider. Out of them, the thermal stability of the voltage divider bias is best, and more number of questions comes in exam on the voltage divider bias only. And we have also understood the concept of the operating point and how the transistor is connected in the different circuits. So I think that's it for this video. We will meet again in the next part of the video, and we will discuss the current mirror circuit. Then we will follow up the AC biasing of the BJT, and after that we will start the field effect transistors. That is the second part of second types of transistor. FET are of two types. BJT, FET are of two types. One is JFET and the MOSFET. So we have understood the BJT, and in the subsequent videos, we will understood what is FET and what is MOSFET. So thanks for your patience listening. Have a nice time and have wonderful time ahead. Thank you.